We are now going to define identification of acids and bases. The definition that we're going to use is known as the Bronsted-Lowry definition. The Bronsted-Lowry definition. And this was developed back in 1923, in which an acid is defined as a proton donor, and a base is defined as a proton acceptor substance. And when we talk about protons, the definition of a proton is a hydrogen plus cation. So when we go ahead and we write down a chemical reaction, we'd like to identify which is behaving as the acid and which as the base. So here we have nitric acid reacting in water to produce hydronium ion and an NO3 minus. A hydronium cation, and an NO3 minus anion. And what we want to identify is which is the proton donor and which is a proton acceptor. When we look at this reaction, if we look at the water molecules, we see that oxygen has 2 hydrogens attached to it. On the product side, hydrogen is protonated, having 3 hydrogens attached to it. Also, we'd like to identify that term. A protonated water molecule is defined as a hydronium ion. So what we'd like to identify in terms of proton transfer in the above reaction, which is behaving as an acid and which is behaving as a base. So we're going to monitor the flow of a proton from the reactant side to get us to the product side. So we see is one of the hydrogens is attaching to the water molecule, forming the hydronium and the NO3 then minus anion. So this is our flow of protons. In this sense, the nitric acid is behaving as the acid and water is behaving as the base. Nitric acid is a proton donor and the water is a proton acceptor. Another way we can look at that here is what's going on is if we draw the Lewis structure for water, the oxygen has two unpaired electrons. And what we have is the proton is transferring and attaching to one of the unpaired electrons on the oxygen, forming the oxygen with 3 hydrogens being protonated, and we're left with the NO3 minus. And this is the definition of a hydronium ion. So that's identifying an acid and the base in terms of nitric acid and water. Let's go ahead and identify another reaction in which we're going to go ahead and react ammonia with water. In this reaction, we're going to produce ammonium ion, in which the nitrogen becomes protonated, and a hydroxide anion. Mind you, terminology, hydroxide, this is what's known as a hydroxide ion, OH minus ion. So we're going to ask ourselves, how do we get from the reactant side to the product side in terms of proton transfer? Once again, what we're going to see here, we have nitrogen with 3 hydrogens on it, and now nitrogen has 4 hydrogens. So if we monitor the flow of a proton, we see that the water is transferring one of its protons, hydrogens, to that of the nitrogen. And in this case, we would identify the ammonia as, we're going to identify the ammonia as being the base, and water as being the acid, proton donor acceptor. And what we're looking at here is in the case of ammonia The nitrogen has one unpaired electron, and from the water, one of the protons is transferring and attaching to the unpaired electrons on the nitrogen, and that gives us the protonated ammonium ion. And then we're left with hydroxide from the water. So what we see in both these cases is that water, or the two different cases, we see that water can readily behave as an acid or a base. And so when that is defined as H2O, terminology is defined as an amphiprotic molecule. What is an amphiprotic molecule? It is one that readily can donate or accept a proton. And water is a good example of that. Now, when we do acid-base reactions, we don't necessarily have to generate a hydronium or a hydroxide, and we still want to monitor the flow of the proton between the acid and the base. So let's look at an example in which neither of those species are being produced. So we have is H2S reacting with a carbonate anion or dianion, forming HS minus aqueous and HCO3 minus. And in this case, we are going to look on the reactant side and go over to the product side, and how do we get from these reactants to these products and monitor the flow of the proton. And what we see here is a hydrogen is transferred from H2S to the carbonate, forming HS minus and HCO3 minus. In this context, not once again, but what we have is H2S is behaving as the acid, and the carbonate is behaving as the base. We have the proton donor, and we have the proton acceptor. And that's using the Bronsted-Lowry definition in terms of identifying acids and bases.